Hello, everyone. My name is Linda Doyle. I'm the Provost here in Trinity, and I'm absolutely delighted to welcome you to this very special occasion where we're celebrating two things. We're celebrating 220 years since the birth of Hamilton, a wonderful Trinity graduate and academic, and 20 years of the Hamilton Maths Institute. So we're very, very proud of our School of Mathematics here, and especially the Hamilton Mathematics Institute, which is run by our esteemed Professor Samson Chattisvilly. So I think Samson is I'm going to hand over to Samson, who is going to tell us about our fantastic speaker for this evening. But I suppose just before doing that, I want to say I think one of the key things that we've been talking about today, and you'll hear now, I think is the value and importance of maths, of abstract thinking, of fundamental research, and the wonderful role that that plays in society. And that's why I think it's especially important to be marking people like Hamilton, who was so utterly fantastic and amazing, and had that incredible ability to think the way he did. So with that, I'm going to pass over to Samson, and Samson will do the honors of the introduction of our speaker.
Thank you so much, Provost. Thank you, everybody, for coming. It seems to me that we calculated correctly the situation. I thank Provost for providing this beautiful venue for such event. I actually did not think about it until Linda said that maybe we do like this. I also want to say that exactly 20 years ago, Trinity hosted a British Association meeting. Actually, Dublin hosted, but the Trinity was a host. And we decided that it was right time to formally launch Hamilton Mathematics Institute, because Hamilton was knighted in Dublin by Lord Governor of Ireland at British Association meeting, which took place in 1845 or something like that. So it was a great thing, so we did it. We are doing okay. I think some of you probably benefit from, I hope, benefit from activities of Hamilton Mathematics Institute. And when we were preparing this event, it was not difficult to decide who should give the public lecture. Because in my view, and I know a little bit about disciplines that Hamilton was originating, there is nobody better than Nigel Hitchin who can talk about impact and today's place of Hamilton's work, because he not only developed it, but he advanced it to the level that there is even a notion of generalized, not quaternionic, but generalized, that Nigel introduced. This just few words about that this was not difficult to decide that speaker should be Nigel Hitchin. Professor Hitchin is a very distinguished It's not working. It's not working. Okay. UK mathematician who was for many years a Savilian chair of mathematics in Oxford, which probably there is no other position in any discipline starting before that, like 1611 or something. Dates that back, 1600 something. Extremely prestigious post, and he was, as I said, for long. He was also involved in developing of the British mathematics in general. Nigel has many, many prizes, and the one special one I always thought was important was London Mathematical Society Prize, that I was told by Arnold that that's the most important one. That I don't know. And of course he has what's called Chinese Nobel Prize, called Shaw Prize, and many other prizes. I think Nigel's teacher was a founding member of board of the Hamilton Mathematics Institute, who is Michael Attia, and I think he was your teacher, if I'm not wrong. And another important thing is that three universities, Cambridge, Oxford, and Trinity College, have very close ties that we recognize formally from ages, each other degrees and so on, and it was absolutely correct choice to bring a professor from Oxford. I think that we will have a fascinating discussion by Nigel of things Hamilton did that not everybody knows. This was important thing, I think, for him to think. And please enjoy our distinguished guest. Nigel, please.
Well, thank you very much, Samson, for that introduction. It's an honor to be here in Trinity and to talk about Hamilton, who has been a hero of mine for a long, long time. But I'm going to talk about, if you like, the mathematics which punctuated Hamilton's life at important moments. So I'm not going to say much about Hamiltonian dynamics, which we've heard about this earlier on, and some of the things which he was involved with have actually mutated into different types of mathematics. And this is the sort of thing that I'm going to be talking about. But it's largely about his life and the mathematics that came out at various points. So let's begin with Hamilton. Okay, well, what about this? Not that Hamilton, this one. Still, you could ask the question, could you write a musical about W.R. Hamilton? And the answer, I don't know. I'm in Dublin. Maybe somebody's already done it. But first, let me say that there's a love story at the heart of it. So let me talk about that first. So here we are, 1824. Hamilton is basically still a student, age 19. He falls in love with Catherine Disney, 5 years older than him. And now, Valentine's Day, 1825, he writes her a long, long poem. So we're going to get used to this. We're going to get used to the fact that Hamilton writes poetry. So if you're going to make a musical, here's the libretto. Yes, Disney. Okay, yeah. But unfortunately, okay, so this is February 14th, 1825. May the 5th, 1825, she's married already. So her family gets wind of this and they clamp down on it. How can possibly their daughter marry a student, 19-year-old student, no prospects? And they've already set her up with this William Barlow, a man with property and income, good connections. So she marries soon after the Valentine. Hamilton is quite upset about this, naturally, and he retains this, well, we can't say, he retains this, it's more than an interest, it retains this feelings for her basically throughout his life. But unfortunately now that she's married, he can't see her. But later on, when he becomes Astronomer Royal in Ireland, he has to visit various places around, and in particular he visits Armagh Observatory, which is close to where Catherine and her husband are living. And so she comes to see him there, and he gets quite nervous. He shows her the optical instruments, and he drops the eyepiece, and it smashes. But worst of all, afterwards he writes a poem about this, and he notices that she's very unhappy. You see, a meek and tender sorrow I have seen. So on the one hand, he was pleased to see her. On the other hand, very sorry to see her in such a bad way. Then, much later in life, she falls ill. She attempts suicide. Her husband forbids her to make any contact with Hamilton until right at the end, when he allows them, or maybe he moves out, and they come together. So this is Hamilton's impression of this final meeting, or several meetings, final meetings. She's, as you see, she's clothes propped up, her languid head. So she's ill in bed, and unfortunately she dies soon afterwards. So this is a story, a very sad story, but it reflects a passion that Hamilton had throughout his life. So it's not really for a musical. I mean, this is more like Italian opera, you know. But what I wanted to say is that he wasn't just a cold, calculating mathematician. He was emotional in many respects, and he had wide interests. But his emotions were expressed in poetry. So instead of keeping a diary or something like that, he wrote poems. And he even published these poems, which is quite remarkable, because if you think about what the husband of Catherine Disney was thinking when he read, if he did indeed read these poems, maybe he just put them to one side. But anyway, this is one aspect of Hamilton's life which I didn't know about until I began to learn about him for this particular task I have to do today. So let's return now. So I should say now at this point that I'm not a historian of mathematics, and so in particular, my sources, if you like, are this biography by Hankins and a biographical sketch of Catherine Disney. And so I'm sure there are members of the audience who know much more about Hamilton than I do. But I hope I get the flavor of his life in what I say in the following. So what about me? Well, I'm a mathematician. I work in geometry. And for me, Hamilton, as his influence has come through one of his most famous discoveries, the quaternions, and also Hamiltonian dynamics. And it manifests itself in my research through the study of what are called hyperkähler manifolds, and also completely integrable Hamiltonian systems. Now, I'm not going to talk about these. It will become too technical. But roughly speaking, hyperkähler manifolds are like doing differential geometry over the quaternions. Some kind of algebraic geometry, but very different from the usual algebraic geometry. So these are the influences that Hamilton has had on my mathematical career. So I've been doing hyperkähler manifolds for 40 years or more. And so his work is very, very important to me. However, we should now return to Hamilton's life. So exactly 200 years ago, 1825, Hamilton gets very depressed. So he loses Catherine, and he fails to get the highest grade here in Trinity. And his first mathematical paper, or essentially his first mathematical paper, is rejected by the Royal Irish Academy. Well, it's sent back for more development. So clearly 200 years ago was a very bad year for him. And he even talks about thinking about suicide. But then, 2 years later, what happens? He's now Astronomer Royal of Ireland. He has a place to live. He has an income. And so, you wonder, I mean, if Catherine had waited a bit longer, maybe, there's a house. But he was unmarried, and so he got his sisters to come and run the household. He had an assistant, and so he was set up in this home, working from home, if you like, in his observatory. But it was an unusual appointment in some respects, because this is what Hamilton says about himself. My tastes are decidedly mathematical rather than physical, and I dislike observing. So, which circumstance makes me rather unfit for holding an observatory. And so, the actual observations, apparently, he did some observations. He had to have training before he accepted the post in observing. But he got his assistant to do most of it, and his two sisters did some of it. And then he acquired a student, came from a distinguished family, who did much more. So how did this happen? How come he became Astronomer Royal without liking astronomy? And the answer is really the papers he wrote on in particular this and the ones which followed on from it. So this was the beginning of a series of papers on the theory of systems of rays. So this was the study of light, which nowadays is called geometric optics. So this is so the idea here. I mean, this is not quite the way he said it, but the idea here is that you look at light rays, the space of light rays, and an optical instrument, so mirrors and lenses and whatever. This is like a black box. So you put in light rays one side, and out come light rays the other side. What goes on in between is, of course, reflections and refractions, but they obey Fermat's principle of least time. So in order to get from A to B through this system, it's the path which takes the least time. So this, in mathematical terms, is a variational principle. But for me, the interest is this the idea of this space of light rays. I mean, he doesn't say it in that way, but essentially this is what he's doing. So you have to think of something which is actually four-dimensional. We've heard about the quaternions. Well, we heard from Jean-Pierre about quaternions being a four-dimensional space which is somehow associated with real life. But in a way, this is also a four-dimensional space which is much more directly associated with the three-dimensional space which is around us. So if you think about the space of light rays, then there are different subspaces of it. So if I have a point, I can look at a point source of light rays. This is a two-dimensional sphere. It's the surface of a sphere. Of course, we can surround that point by a sphere, and then we can say, well, each light ray emitting from that point intersects it in one point. But this is the sphere. That's a sphere in this space. But there is a sphere. But if I take a bigger sphere, I'll still parameterize the same light rays. So this space of light rays includes a lot of two spheres, a lot of two-dimensional spheres, which correspond to the points of our three-dimensional space. But there's also a family of two-dimensional planes. If we look at the parallel beams. And so in technical terms, in mathematical terms, this space of light rays is a four-dimensional differentiable manifold. And it's, for those who know about these things, it's the space of tangents to the two-dimensional sphere. So this is four dimensions. We have two dimensions, if you like, for the direction, and two dimensions for the plane that they hit. So this, to me, is the idea of using this. And of course, the optical aspect of it was, it introduced the idea to him of using the mechanical analogy as well. So it was the optics that came first, in Hamiltonian dynamics, where you use a variational principle for the action. That was kind of derived from the optical picture. So to me, this idea of describing objects in our everyday space by something four-dimensional and describing them geometrically is a very radical thing to be doing in those days. So now, some years ago, I actually, working on another problem, what are called magnetic monopoles, I came up against this space of light rays as well, and I noticed that you could describe it in terms of not just four real coordinates, but two complex coordinates. And so in this case, if you fix a coordinate psi, then those are the parallel light rays, and this formula down here tells you that if you take a point in three-dimensional space, this is the formula that describes the spheres. So this was to do with a different problem, nothing to do with optics. But it was picked up on by actually, okay, I introduced this because it appeared in an Irish publication. It was picked up by these two authors who actually used this complex description to describe what Hamilton's characteristic function. So this was you take 2 points and you look at, if you like, the time. You have an optical system and you look at the time a light ray takes from going from X to Y. And this, one of Hamilton's insights was that if you know this function, then you know the paths, whatever happens, you know everything about a light ray that comes in from the left and goes out from the right. So you have a space, you have a function, and then in principle, you know what happens to light as it passes through this optical system. Now, in this paper, they actually do computations, and I'm just picking out a particular formula. I don't expect you to read it in any detail. The point is that this V, this function, is actually difficult to determine. And so if you actually want to solve particular problems, then you have to use other methods, geometrical methods that replace this. So it's a philosophical idea. Of course, the more it was developed with mechanics and so on, it was expressed in different equations. But this particular approach kind of demonstrates that actually, philosophically, it's interesting to know that this function determines everything, but actually finding it in a particular instance is difficult. So this began his work as theory of systems of rays, and as I say, he followed it up with other associated papers, and he dealt with reflection, refraction, as you see, aberrations, all these optical phenomena. And that was in 1824. So he began this in 1824. But now, see what happens. In 1832, Hamilton has all these letters after his name. He's now, you can see them all, member of the Royal Astronomical Society, honorable, whatever, British Association, fellow of the American Academy of Arts and Sciences. I'm coming to that. Yes, so his work, which stemmed from this geometrical optics idea, extended, and he became famous, basically, by 1832. And in fact, 1835, he's given the Royal Medal of the Royal Society. This is a citation, papers published him in the 16th, okay, here we go, entitled Supplement to an Essay on the Theory of Systems of Rays. And as you see, there's a famous third and last supplement, which relate to the discovery of conic refraction. So what is this? This is something which nobody nowadays thinks very much about. But it was important in those days, and it's mutated over the years into some very interesting mathematics, actually. I won't say the actual phenomenon of conical refraction, but the mathematics that it involves. So I want to tell you a little bit about that. So first of all, well, I think we all know what refraction means. So if we have a block of glass here, and if you have something which is, so a block of glass is an isotropic medium, so the velocity of light in any direction is the same, but if you have a crystal which has an axis of symmetry, then there's this phenomenon of double refraction. And so here's a diagram of what happens. So a light ray goes in at one side of the crystal, and then it gets split into two rays, depending on the velocity of light in a given direction is different. So the refraction causes the light ray to bend in different directions. And if we look now further at a crystal which doesn't have just one axis but has two axes, then it was Fresnel, a French physicist, mathematician, who actually derived an equation for this. So this is nowadays, or in those days, was called Fresnel's wave surface. Or I'm not a physicist, so I'm not quite sure whether it's a wave surface or a ray surface. It's a question about velocity. Is it group velocity or wave velocity? Maybe people in the audience will know this. But anyway, here is this surface. And what it does is, so it gives you the velocity of light in a medium, so these AIs depend on the physical properties of the medium, and this equation gives you the velocity of light in a given direction, if you like. I mean, the velocity, velocity has the direction, so it's the speed in a given direction. And algebraic geometrically, this is a surface of degree 4, so we call this a quartic surface. And if you plot it nowadays using Mathematica, then this is what you get. So the important thing about this is that you see it's got two shells, and that's where the double refraction comes from. So if you take a particular direction and you want to think about light going in that direction, then you have to think of a plane perpendicular to that direction coming down, meeting that shell at one point, which gives you one velocity, then it passes through and meets the other shell at another point. And that's the phenomenon of double refraction. But there's something extra about this. So you don't see it so much for that one, but this is one of these 19th century plaster models of this surface. So they've filled in, they've filled in the gap between the two shells. And what you see there is that if you bring a plane down to hit this surface in a particular direction, then you see a circle, not just a single point. So this means that the refracted rays, if they're coming in a particular direction, they come out in all those directions corresponding to that circle. So this is conical refraction. So if we go back, you can almost see it in this picture. So if you like, those are called nodes. Those are singularities there. You can also almost see that you can push your finger in. There's a little dimple there, so you can imagine the plane. But it's much clearer in this 19th century model. So this was something which gave rise to, theoretically, to conical refraction. So what did Hamilton do? He looked at his colleague, Humphrey Lloyd, and Lloyd ran some experiments. At first, they didn't work, but pretty soon he discovered that you could get, through certain crystals, you could get this conical refraction. So this was a big deal in those days, and in fact, here's a couple of quotations. So George Airy says, this is the most remarkable prediction that has ever been made, and Plucker in Germany, no experiment in physics ever made such an impression on me. So I think it's one of these early examples of a theoretical result which is verified experimentally. Not only that, but within a few years of the theory being discussed. It was compared at the time to the discovery of a new planet. Nowadays, I think we wouldn't be so impressed, perhaps. But anyway, it was what led to the Royal Medal and subsequently to the knighthood for Hamilton. So, but let me follow this up a little bit, because that quartic surface leads us to a particular type of object in algebraic geometry and in other areas which has attracted a lot of attention. It's attracted a lot of attention after Hamilton's discovery. So here's a list of 19th century mathematicians who actually took this up. They looked at quartic surfaces, they looked at this particular quartic surface, but they changed the coefficients a little bit and looked at other quartic surfaces. What they also did, this was something which was emerging in the early 19th century, was that you don't work with real numbers. Life is much, I wouldn't say easier, but you see structure easier when you work over the complex numbers. And what they discovered was that what we saw in the model there was 4 singularities, 4 nodes, and 4 planes which cut in these circles. That when you work over the complex numbers, you get 16 nodes and 16 planes, and each plane meets 6 of these nodes. So this is a combinatorial expression. It's what's called a 16-6 configuration. So this this is a systematic way of thinking about this. So you have 16 objects and 16 other objects, and there's some relations between them. So in this diagram here, on the left, you see 16 black dots, but there are also 16 pairs of rows and columns. You know, 4 rows and 4 columns. And if you look at the points that if we remove the point in the cross, you have 6 of those black dots which lie there. And now when you look at the intersection of 2 of these 16 objects, you see they intersect in 2 points if we forget about 2 points if we forget about the center of the cross. Well, and in terms of the geometry, it means that we have a pair of these 16 planes. They define 2 of these nodes, and there's a line that joins 2 of these nodes, a line that joins 2 points. So that's the intersection of the 2 planes that meets those points. So this is a schematic description. You can do it the other way around. You could think of the pairs of row and column as being the 16 objects and do it the other way around. It's a very interesting combinatorial configuration. But then the work went even further. So Weber, in 1877, he actually gave, if you like, a solution to this equation, a parameterization, which some of you may recognize as involving Jacobian elliptic functions. So what these are periodic functions, and which have a certain property. So you have a pair of periodic functions. How do you describe a pair of periodic functions? Well, a single periodic function, you can think of having a period. Let's say, well, a doubly periodic function you can think of being defined on a rectangle, or if you like, you could identify the sides of the rectangle to make a torus, a donut shape. But in this case, what happens is that we're looking at the original surface, we're looking at real points. And real points means real coefficients, but if we're identifying u and minus u, that means that imaginary coefficients are also regarded as, they also map down into real points. So the point is that the 2 sheets which we see in that picture are really coming from these two parts of a doubly periodic object. So this was an observation that came from Weber, but it was carried forward, and well, you might say, here, what am I doing here? Here, let me say that so far I've been talking about what happened at the end of the 19th century. You might ask, well, did people continue to be interested in these kind of quartic surfaces? Did it stop at the end when the 20th century began? And the answer is no, but in fact they're currently of great interest. And what I've done here is list some of the papers of one of your professors here in Trinity College, where Catherine Wendland, where she's talking about Kummer surfaces, K3 surfaces, Kummer K3. These are all examples, maybe not quite, but they're related to these quartic surfaces that emerged out of the conical refraction of Hamilton. So nowadays, these are used to define certain conformal field theories in theoretical physics, but they're of great interest, great studies. So as I say, conical refraction per se is not regarded nowadays as a big deal, but quartic surfaces and their generalizations, Kummer surfaces, K3 surfaces, are very important. So that's one strand, one piece of the legacy, if you like, of Hamilton, which you might not appreciate otherwise. Okay, well, let's get back to Hamilton himself. So where were we? So he gets this Royal Medal from the Royal Society, 1835. As we've heard, he's knighted in 1835. His collaborator, Lloyd, gets Fellowship of the Royal Society, 1836. And what about Hamilton? He doesn't. So you might ask the question, why doesn't Hamilton get elected as a Fellow of the Royal Society? After all, he's won the Royal Medal. And I don't know what the answer is, but one answer is that maybe he didn't want to. Of course, he was involved with the Royal Academy here, the Royal Irish Academy, but also at the time, the Royal Society was, there was a lot of criticism about the Royal Society. So there's a diatribe that was produced by Charles Babbage. So Babbage was the man who created this physical computer. You might see it, I think it's in the Science Museum in London. And he wrote this diatribe on the decline of science in England, and as you see, the great and leading cause of the present state to which the Royal Society is reduced may be traced to years of misrule. So maybe Hamilton preferred the Irish Academy to the Royal Society. Anyway, this is what Babbage. So this is Babbage's view here. So okay, at the time, 1835, who was the president of the Royal Society? The Duke of Sussex. So you can't imagine nowadays the Duke of Sussex. That's Prince Harry being president of the Royal Society. So this Duke of Sussex is the uncle of Queen Victoria, not a scientist at all. And here is Babbage's view of the election process. So I don't know whether you have time to read this. So he's being ironical, of course, but you see, if on the other hand he has unfortunately written on any subject connected with science, the members begin to inquire, what has he done to deserve the honor? And unless he has powerful friends, he has a fair chance of being blackballed. So I think the election to the presidency of the Royal Society has changed, and I hope that the other part has changed. But I don't know whether you saw in the news that I think a couple of weeks ago there was quite a lot of discussion about whether it was right to have elected Elon Musk as a fellow. So he still is a fellow. The procedures went through, but clearly it was a controversial issue. Anyway, so the Royal Society had become in disrepute. And what Hamilton did do was to become part of a new organization, the British Association for the Advancement of Science. So this was founded in 1831. They had a small meeting in York, and they followed it up with a bigger meeting in Oxford. And Hamilton attended this, representing the Royal Irish Academy. And he gave a long speech. These speeches, they're very flowery language, but as you see, what he says is that assuredly must the hearts of Britons and Irishmen be more and more knit together in affection by the fraternal intercourse of their minds in this intellectual and national assembly. So actually what he went on to say was that he saw Irish and Britons as being like Spartans and Greeks. So, in other words, they spoke the same language. Maybe they had a little fight now and again, but that here this was like coming to the Olympic Games and fighting and competing together. Anyway, he was representing Ireland most definitely in this, and in fact, so he followed it through. He would use the meetings of the British Association to introduce his new ideas in mathematics. So, okay, in Cambridge, 1833, it was conical refraction. Edinburgh, it was the dynamics. Then he persuaded them to come, after going to Scotland, to come to Dublin. This was when the Lord Lieutenant gave him his knighthood. And then in Newcastle, it was talking about the propagation of light. It came back to Ireland in Cork in 1843. And then in Oxford, 1847, he's talking about quaternions. So now we come finally to quaternions. And what do we know about quaternions? Well, this is the famous story of Broome Bridge and the walk. So I'm sure many of you in the audience know about this. So Hamilton and his wife were walking to go to a meeting of the Irish Academy, and he'd been trying to understand an extension of the complex numbers which would be used to describe 3 dimensions. And then when he saw that bridge, when he passed that bridge, he had a flash of insight about the relations between these objects, what they should be. So this was October 16th, 1843. So actually there's a canal near my house, and there's a bridge on the canal as well. So this is my bridge. You say I don't have as many graffiti as you do, but there's no plaque. So actually, a couple of years ago, I was walking along there, as usual, thinking about mathematics, and I did have a good idea, I must admit. And so it turned out to be October, and I looked at the date, but it wasn't October the 16th, so it didn't really count. Anyway, the story is that Hamilton scrawled on the bridge these famous equations for quaternions. And so this is what the one at the top is what he reputedly scratched into the bridge. I have a feeling he wrote it down on paper as well, but because he went on to talk about it. So I think he was president of the Royal Irish Academy at the time, and so he was allowed to change the talk that was going to be given, and he introduced the quaternions. So a general quaternion is some combination of these where you have real numbers as the coefficients. And the key point about these was that if you multiplied p by q, it was not the same as multiplying q by p. And so in the context of the time, this was, both of these aspects, the fact that p times qr is the same as pq times r, these were times when there was a movement. So earlier on, how should I put it? It's like, what were you allowed to do in algebra? So it's almost like a child at school who was introduced to the complex number, the I squared equals -1, and says, sir, are we allowed to do that? And so, in some sense, I think algebra in the early 19th century was only gradually developing away from the idea that the symbols represented numbers. And if you move away from that, then you have to ask yourself, well, what relations hold? Do we carry on with, which rules do we maintain? Which ones do we not keep? And I think this idea of that associativity, as we call it, P times QR equals PQR, that was an important feature, and the fact that PQ is not equal to QP also. So it was radical in the sense that if you like, you can experiment in any direction you like, but you have to have some consistency. And so the quaternions were really one of the first situations where there was everything fitted together. In Hamilton's books, where he gives a long account of these, he goes into a great deal of detail proving that these things hold, these relations hold, not just by expanding things and using the formulas, but by having some geometrical interpretation. So he was very, very keen on justifying that you are allowed to do this. So the key point, of course, about the quaternions was that if you have a quaternion which is not equal to 0, you can invert it, and here's the formula for its inversion. On the other hand, so for most of the rest of Hamilton's life, he spent working on quaternions, and not everybody liked them. In fact, to be honest, very few. So the first is a quotation, a contemporary quotation, well, not contemporary, this is later in the 19th century. As you see, Lord Kelvin, famous physicist, he summarizes the situation that he sees it, that the quaternions were beautifully ingenious, but have been an unmixed evil to those who touch them in any way, including Clerk Maxwell. Here is a quotation from there was a paper about the quaternions written by physicist Simon Altman, who was in Oxford. And he has this rather, how should I call it? They exude an air of 19th century decay as a rather unsuccessful species in the struggle for life of mathematical ideas. So there was a dispute about how you could use the quaternions. And in fact, so Hamilton wrote a long book of lectures of quaternions, and he made this rather bitter comment. When he said that Dublin was not a book-buying place, perhaps he spoke with them on account of its not having bought any copies of my own book. So I thought, well, in preparation for this lecture, maybe I should see what Oxford has. You know, does Oxford have a copy? And it turns out that they do, but I found it in the library of the Oxford Union Debating Society. So this is the library, okay? So when we talk about an air of 19th century, this is it. Whether any, future prime minister was interested in quaternions, who knows? I mean, I do know, of course, that Eamon de Valera here was very interested in quaternions. But whether that happened in Oxford, I don't know. So, okay, so that's one aspect of quaternions. On the other hand, if you now look at Wikipedia, this is what you have. You can read that it's had a revival since the late 20th century, primarily due to their utility in describing spatial rotations, and in particular in attitude control systems of spacecraft. So what does that mean? So attitude. So really, this is a question of rotation of axes. So if you have a satellite like this, then you may need to direct the solar panels towards the sun. You may need to align it with certain features on the Earth, and so you need to know it has these axes, and you need to know how to rotate these axes. And quaternions help you to do that. And so here's the point. The point is that a rotation, it has an axis and it has an angle. So the axis is a unit vector and there's a rotation by an angle. Then if you write down this quaternion, so you use the angle, and this E1, E2, E3 these are the components of that unit vector E. Then that quaternion has a very nice property that if you multiply using quaternion multiplication on x, so x is now what we call an imaginary quaternion. So we take a point in 3 space with coordinates x1, x2, and x3, and we write down this so-called imaginary quaternion. And if we do this multiplication by this expression, then that's the effect of rotation by an angle of theta. Not only that, but if you multiply these two quaternions together and using the rules, I squared, j squared, etc., then it's the same as having one rotation followed by another. So this is a very simple way of composing rotations. On the other hand, it involves this half angle. And this, to me, is something which, so I looked quite extensively through these lectures on quaternions. In fact, okay, I said the only copy that exists in Oxford is in this library, and it kind of falls apart when you open it. But there's one online, so you can actually read it. I found that he didn't really appreciate the ambiguity in this half angle. That in some sense, it's very important because there's an ambiguity of a plus or minus 1 or if you like, adding on pi. Because if he'd seen that, then he would have perhaps not tried to do with the quaternions what he did. So he wanted to use the quaternions, this four-dimensional space of quaternions, in some way to describe operations that we do in 3 dimensions, in mechanics and physics and so forth. And if he'd really understood that half angle, then he would have discovered spinors, electron spin. Of course, he couldn't. I mean, there was no experiments which told you what electron spin was, but the half angle there is really, if he'd really paid attention to that, then I think he might have changed his ideas about what quaternions were really good for. However, they are good for understanding rotations. And in fact, this is one way in which more recently they've been used. So a quaternion which looks like this, so if we look at the coefficients, then we see the sum of the squares is equal to 1. So this, to a mathematician, this says that this is the equation of the surface of a 3-dimensional sphere in 4 dimensions. On the other hand, how can we visualize a 3-dimensional sphere in 4 dimensions? So you have to do it by analogy. So what I've drawn here is a picture of a 2-dimensional sphere in 3 dimensions. And I'm trying to show you that you can project, if we look at the North Pole and we draw a line through that, every point except the North Pole can be parametrized by a plane. So so what are you looking at there? You're looking at actually a 2-dimensional picture of a 3-dimensional object. So if you can extend your intuition a little further, then you have to think of this 3-dimensional object, this 3-dimensional sphere in the 4 space, as look at the same construction. You look at -1 as the North Pole, and you do the same construction, and then you can project onto not the plane, not that tabletop there, but on a 3-dimensional space, which is the space around us. So if you ignore the plus and -1, so then actually you can represent a rotation by a point in 3 dimensions. You can in a way you express it twice because of this plus/1. So that actually is a key point to a more recent use of quaternions. So this is what is this for? This is for plotting rotations, or if you like, plotting configurations, frames, orthogonal frames, axes, like the axes of the satellite. And this has been used for protein molecules. So here is a picture of a protein molecule made up of these pieces, these amino acids, but each of those pieces has 3 axes. So this is a picture of the, if you like, of the actual points of the molecule. But for various reasons, you want to know about how are the orientations of these parts varying. So here is a way in which you can plot these. So this is so the picture on the right, these dots on the right, are the orientations of the individual parts of this protein molecule, but using a projection from the 3-dimensional space of unit quaternions onto a 3-dimensional space that we live around us. Of course, it's a 2-dimensional representation of it, but we've learned to understand this as a 3-dimensional object. So this is another approach to using quaternions. And I'm putting a plug in here for this book on, there's a second version of this as well. This is called Visualizing Quaternions. and I should perhaps I could say that Andy Hansen here, he began life as a physicist. One of the things which he in the 1970s, one of the things which he actually and another physicist, Eguchi, discovered was one of the first examples of these hyperkähler manifolds that I've been talking about. I've been saying that I'm interested in. But he left physics and moved into computer science, and now he's written many papers and books on this visualizing quaternions. So this is what the quaternions have become. They're no longer a 19th century object. They're very much a 21st century object. And so one could ask, what would Hamilton have thought about this? Would he be impressed? And I don't think he would, actually. I don't think he was interested in technological applications. I mean, his interests were more philosophical. So he was interested in the quaternions in the same way that he was interested in the complex numbers. And in fact, he had a whole philosophy about the science of pure time, even the idea of ordering of the real numbers. He thought of that in terms of time. He tried to advance that into complex numbers and quaternions. So he really wasn't interested in technological applications. In fact, at one point, George Airy, who was the Astronomer Royal in England, he mentioned to Hamilton, he said, isn't the Liverpool to Manchester Railway, isn't that one of the greatest creations of science? So this was the first real railway, with architect designed stations and so forth. And Hamilton dismissed that completely. No, the applications were not his interest. So this comes back to his work is basically on fundamental science mixed with philosophy. So as we've heard, he was a poet as well, and he even befriended Wordsworth and Coleridge. Wordsworth was much older than him, but they talked a lot. Wordsworth persuaded him, or tried to persuade him, to concentrate on the science rather than the poetry. But they talked a lot, and they talked in philosophical terms about the philosophical meaning of the things which he discovered. So it's remarkable then that actually these fundamental objects which emerged from Hamilton's life have such an important legacy today. So, thank you.
Thank you so much. It was wonderful. I learned. I thought I knew almost everything about Hamilton, but I learned many things here. We take questions, of course. Please, any question for Nigel?
Okay.
Yes, please. Andrea. You, Andrea. Yes.
Yes, that'd be good because, as I said before, there are many here who know more about Hamilton than I do.
I was just going to say that in graph theory, he introduced a notion of a Hamiltonian path and circuit when you're visiting each vertex of the graph exactly once. And he monetized that by creating a peg game. I think it was maybe in the 1850s. So he didn't make money on that book on the quaternions, but he apparently made money on this game.
Yes, I read about that too. Yes, Hamiltonian
Thank you,
circuits,
Andrea.
of course, we have. There are other things that Hamilton did, but these are perhaps...
Other questions, please? Actually, I noticed. Yes, please. Wait.
So what was the question again? Okay, I think the microphone is coming.
What made quaternions unsuitable for what he wanted to do with them?
Well, it was this argument. Well, the question is, do you have to use quaternions, or could you use what we now use called vector calculus, or vector operations? What he did do was to approach. He actually defined what we now call vector spaces. He knew that you could add rows of numbers, and he even used the terms scalars and vectors. So when he began to introduce quaternions, there was a question about the real part and the imaginary part, the coefficients there. He called at first he called the real part a number, and the other part a line. So this was, but then he changed it because that didn't make sense. He changed it to scalar and vector. So he introduced the words scalar and vector. And then he also actually described how you could do this in higher dimensions, but without the multiplication. And I think so. The point was that I think he tried too hard to reformulate equations which were perfectly well formulated in terms of what we would call cross products and dot products. Or in those days, maybe it was using direction cosines and so forth. But trying to force the quaternions to do what they weren't really well adapted to do. As we know nowadays, the quaternions are spinors essentially. If you act on them on the left by unit quaternion, that's the spin representation of SO3. That's something which he didn't really, I don't think, really appreciate. So he was trying to understand how to use them in 3 dimensions as a substitute for what we now use in terms of vector calculus.
Okay, other questions? Yes, Luke?
It's worth pointing out that Hamilton's good fortune was that Trinity was in advance of Cambridge and Oxford, in that when he started his studies, they had already switched to continental mathematics, whereas Oxford and Cambridge were still fixated on Newtonian's Fluxionion, which was very regressive, really, and inflexible. So in many ways, the continental influence was actually crucial for his work. In some ways, he built on the work of Monge and as you mentioned, Lagrange. But what is interesting about Hamilton also is his strong sense of having an Irish identity. You mentioned that he never applied for membership of the Royal Society. One speculation is that he couldn't afford it. He always had problems with his finances. He was never very good with money. And that might have been an influence, but clearly he thought of himself very much as an Irish intellectual. He was very clear that his work would bring honor to Ireland. He mentioned that several times. The question, I suppose, is really, was this a factor in his not seeking membership of the Royal Society, do you think?
Yeah, I think it probably is. He might have been saying to himself, what, more committees? I've got enough with the Royal Irish Academy. But you're quite right that it was the continental mathematics that really he was absorbing. And I think it was, how did he obtain this? It wasn't as if the Royal Irish Academy, their publications were taken by the universities around Europe. So, but he was. But you're right. I think the English tradition was more fundamentally based on Newton until much later. And
somehow I heard from a long time ago, I don't know, maybe David Wilkins or David Spearman, someone, that he had alcohol problems, right? And I was told that he wrote a letter to Royal Society, "You're too expensive." I don't know, I heard something like that. Other questions, please? Yes, Marvin?
Yeah, so I have a non-math question. How was Hamilton's poetry? Is it worth reading beyond him being Hamilton? No? Okay.
Well, I'm a mathematician, not a poet, but I did download a paper which was an appreciation of it. So, but he was warned against it not just by Wordsworth, but also by. So there's a family, maybe people know this, the Edgeworth family, a very important family here, which he made contact with. And Maria Edgeworth was a novelist, and she told him that she didn't like his poetry either.
Okay. If
But
I may,
but on the other hand, it was a way of expressing himself. You know, instead of writing a diary, he would write this.
if I may make comparison, I think his poetry was like Einstein's violin.
Okay.
Other questions, please? Yes.
If I understood correctly, you're saying he had sort of a slightly near pass with twistor theory, you know, considering the light rays as an object themselves. How close did he get? You know, how near a pass was it?
Well, I mean, as you know, twistor theory is one way of looking at quaternions in a geometric way. So it's where you think of not ij and k, but you think of a combination of ij and k whose square is -1. So he noticed that if you take an imaginary quaternion of length 1, so that's a two-dimensional sphere, sum of the 3 squares is equal to 1, then it corresponds to something which squares to -1. And he refers to quite a lot in his lectures. So and the idea about these hyperkähler manifolds is that you should not try and find quaternionic coordinates in the same way that you would find complex coordinates for a complex manifold. But you could try and do it for one complex structure at a time. So he does discuss this. I mean, not that nonlinear geometry of hyperkähler geometry, but he does discuss the fact that you get a lot of elements that square to -1 from looking at this two-sphere. Yeah, that's right. So, but I don't think we could imagine him inventing twistor theory in that formalism anyway. It's too nonlinear.
Okay, we can take a couple of more questions if someone wanted to ask. Okay, actually about twistors, I should say. Now, one of the first Hamilton lectures here in Royal Arch Academy has Hamilton lectures. About 20 years ago they started, or 25 years ago. So first one was Murray Gell-Mann. Murray Gell-Mann.
Yeah.
It was a good choice to invite Murray Gell-Mann, and I took him to the Danzig Observatory for clear reason. And so I asked him to give some little lectures there. And he did, and he said, at the end of 10-minute speech, he said, everything he did was great, but who needs these quaternions? You know, completely useless. I mean, he's a Nobel Prize winning great physicist, Murray Gell-Mann. And I was sitting I was just hired here, just like 2-3 months before. I came in July probably, and this lecture was in October, like we do it in October because of quaternions. And I raised it, no, you're wrong, you know, what about Penrose? I said, what about twistors? What about instantons? Right? It's all the physics that where it shows up. And he says, first of all, Penrose, not physicists, not mathematicians, we don't discuss. He might do the tiles, it's his business. Second of all, what is instanton? He asked me. I was so ashamed, you know, I didn't know what to do. So I stopped, I didn't ask him. But other thing I should say is that from your thing, what you said, it's impressive in today's world to think that, I mean, he was a star in his time, it's clear. He was not only star, I mean, James McCullough probably was also some kind of star, they were together. He was a star, but he was loyal to discipline. You know, as you said, he never did anything which had applications, right? I was told by many of my friends that probably he was first theoretical physicist because he did not do applications, he did not do experiment. Everybody before, like Faraday and Newton and so on, would have something done apart just theoretical, right? Did something else. So he probably was the first theoretical physicist. Peter Goddard told me this is the time when English universities were invented the titles, theoretical physics professorships, when they start dividing natural philosophy into parts. Probably was true. But Peter Goddard had the theory that, end of 20th century, the same things they are connecting now. They're creating schools out of departments and asking to be interdisciplinary. So these things happens, right? This is the first thing, loyal to discipline. And second, he was loyal to Trinity. He could have gotten probably any offer.
Yes.
I mean, in today's world, with this kind of results, he could have been in Paris, in Berlin, in London, in Cambridge, Oxford, and so on, right? Anywhere.
Yeah.
But he came at 15-year-old at Trinity, and he died when he was 60-year-old at Trinity. That's kind of interesting, right? I mean, absolutely some things that we call today theoretical physicists that, I'm one of, I like to be like that, this is a dream. So these two things are interesting in Hamilton. But why Murray Gell-Mann did not appreciate quaternions, I think many physicists don't appreciate quaternions. And Michael Atiyah, your teacher, Michael Atiyah, said that nabla, the gradient operator, is a Dirac operator.
Yeah.
It's a Dirac Hamiltonian. So it's not just, and because of that, because of Michael, when we created a coin, Ireland created the coins in his 200th anniversary, and I insisted nabla to be on one face.
Okay.
So nabla is, but he missed spinners, right?
Yeah.
So probably if there are no questions, we can close and thank Nigel again.